tonight, we're going to leave the solar system, or at least, that's what it feels like. We're going to rise above the planets, dive below them, and pull back until that familiar classroom poster shrinks to a tiny, glowing diagram in the dark. You know the one. The flat picture of the solar system with the sun on the left, the planets in a neat line, and Pluto sulking at the edge like it's guarding the border of everything. Because here's what nobody tells you. The moment you try to go above and below that picture, the whole thing falls apart. In space, there is no up, there is no down. There is no top of the solar system or bottom of it. There is only motion and orbit and gravity, all tangled in 3 dimensions. And yet, something is above the planets. Something is below them. Not just a few tilted orbits or a stray comet here and there, but an entire hidden architecture that your textbook diagram quietly erased. Look at that mental poster again. Past Neptune, past the Kuiper Belt, your brain probably fills in a simple answer. Empty blackness. A kind of cosmic parking lot where the solar system ends and deep space begins. That last planet feels like a finish line. Cross it, and you're out. So here's the paradox. Voyager 1 has been flying away from the sun for nearly 50 years. It's more than 160 astronomical units out, so far that the sun is just a bright star behind it. NASA calls it interstellar space because it has slipped beyond the heliopause, the bubble of charged particles the sun blows into the galaxy. That sounds like we've escaped. And yet, by the real measure of the sun's reach, Voyager hasn't even crossed 1% of our star's gravitational territory. So, let's start at the very beginning of that territory. The true solar system doesn't stop at Neptune's orbit. It doesn't stop at Pluto or the Kuiper Belt, or even at Voyager. It swells outward into a vast, invisible frontier called the Oort Cloud, a spherical halo of icy worlds that could stretch nearly a light year in every direction. Trillions of frozen bodies, most no bigger than mountains, wrapped around us like a ghostly shell. If the solar system were a city, the planets would be downtown. Voyager would be loitering in the outer suburbs. The Oort Cloud is the dark countryside beyond the last streetlight. So far out that passing stars and the gravity of the Milky Way itself start to tug on those distant orbits. Now let's begin to peel back that flat poster and replace it with what's really there. Because by the end of this journey, you won't think of the solar system as a thin disk with a tidy edge ever again. You'll see it as a 3-dimensional bubble of worlds floating inside an even larger cosmic structure that we've barely begun to leave. So if Voyager hasn't really left home, where does home actually end? It turns out the place we call home doesn't end where you've been taught it does. The last planet is not the edge of the solar system. It's the welcome mat. Neptune, that tiny blue marble on the far right of the classroom poster, is just the last bright porch light. Beyond it, the Kuiper Belt is like the cluttered front yard, and past that, you step off the driveway and into a vast, dark countryside that almost never makes it into the picture. Because here's what nobody tells you. The diagram stops long before the solar system does. So let's start at the very beginning of this illusion. Those neat flat orbits you've seen, they only show you out to about 30 astronomical units. 30 times the distance from Earth to the Sun. Voyager 1, our protest little robotic explorer, has been flying for nearly 50 years and has just passed 160 AU. That sounds huge. Until you put it next to the Oort Cloud. The Oort Cloud doesn't sit at 50 AU or 100 AU. The inner edge is thought to begin around 2000 AU, and it may stretch to 100,000 AU from the Sun. That's roughly 1.5 light years. If the distance from the Sun to Neptune were a single step, the Oort Cloud would be the length of a city. Suddenly, every textbook diagram you've ever seen is not wrong, but it is hilariously zoomed in. And this is where it gets emotional. We like to say we've left the solar system. Voyager has crossed the heliopause. It's out in interstellar space, and that sounds final. But in terms of the Sun's gravity, in terms of the true extent of our home, Voyager hasn't even cleared the front porch. It hasn't crossed 1% of the distance to the outer Oort Cloud. For a spacefaring species, that's a humbling thought. Inspiring, yes. But humbling, because wrapped around those flat planetary orbits is something eerie, a ghostly sphere of icy worlds, above and below the plane, all the way around us. Trillions of frozen bodies, most no bigger than mountains, all loosely bound by the Sun's gravity out in the dark. And yet, something is above the planets. Something is below them. These objects don't care about the tidy ecliptic. Their orbits are tilted in every direction, some even retrograde, forming a three-dimensional shell. Out there, the Milky Way itself pulls and tugs. Passing stars brush by. Galactic tides slowly shake this cloud, and every so often a distant ice world is nudged onto a long, plunging path inward, becoming a long-period comet that suddenly appears in our sky. That beautiful glowing visitor? It's a message from the borderlands. Now let's begin to see the consequence of all this. If the true solar system extends nearly 2 light years, what does it really mean to leave home? Where is the border if the Sun's influence fades gradually into interstellar space instead of ending at a line on a poster? Once you feel that scale in your gut, it changes how you think about exploration, about safety, about what counts as far. And we've only talked about distance. We haven't even unfolded the full 3-dimensional shape of this cloud, or how we discovered it without ever seeing it directly. And that's the wild part. We're talking about the largest structure the Sun owns, and we've only sketched the outline. If that picture of a hidden, spherical cloud hanging above and below the flat planetary plane is doing something to your brain right now, this is the perfect moment to ask for a tiny favor. If you're into this idea that our neat poster solar system is just the thinnest slice of a much stranger 3-dimensional reality, tap like, and consider subscribing while you're already here. Because here's what nobody tells you. Those clicks don't just feed an algorithm. They change what kinds of questions we can afford to chase. Deep dives into the Oort Cloud, the heliosphere, the Sun's Hill sphere, the way galactic tides quietly tug on comets a light year away. Those take time. They take simulations, papers, cross-checking numbers so we're not just waving hands at the dark. When you interact, you're effectively voting for more of that. You're telling the platform and us that you want the big, weird, research-heavy side of space. Not just another tour of the 8 planets you already know by heart. You know the one. The flat diagram where everything important stops at Neptune, like there's a decorative border around the solar system. So here's a question for you, and I'd love to see this blow up in the comments. Before this video, what did you imagine the edge of the solar system looked like? Was it a hard shell, a fading glow, a line where the Sun's gravity just quits? Or was it simply the last planet, as if Pluto were the cosmic doormat and beyond, that is, outside? Drop your picture in a sentence or two. When you write it down, you're not just helping the video, you're planting a flag in how you think about our place in space right now, before we stretch it. And we actually read those. They shape what we tackle next, which models we animate. which misconceptions we tear apart on screen. In return, here's what we're going to do for that click. We're going to give you the full tour from the inner planets, through the asteroid belt and Kuiper Belt, past where Voyager 1 has slipped through the heliopause at only about 160 astronomical units, all the way out toward the sun's true gravitational frontier, brushing the inner edge of the Oort Cloud thousands of AU away. We'll rebuild the solar system from a thin poster into a layered, almost city-sized map in your head, so you can feel why we've barely left the suburbs. Alright, let's zoom out and rebuild your picture of the solar system from scratch. So let's rebuild that picture in your head, not the real solar system yet. The poster version, the one that's been quietly training your intuition since primary school. Now let's begin with the classic top-down diagram. You know the one. Sun in the center, a perfect glowing circle. Around it, neat rings like someone took a compass and a pencil to the page. Mercury, Venus, Earth, Mars, all tracing almost perfect circles on a single, flat sheet. No hills, no bumps, no above or below at all. Just a cosmic dinner plate floating in black space. In your mind, shrink the planets down to something you can touch. Mercury is a tiny metal bead. Venus, a cloudy marble. Earth, a blue-green marble with a glossy finish. Mars, a dusty red marble. We line them up on a table. We draw their orbits as chalk circles right on that tabletop. You can run your hand across the surface. It feels perfectly flat. Every orbit stays glued to that plane. Farther out, we place a bigger striped marble for Jupiter, another for Saturn with a razor-thin ring drawn around it, then the pale ice marbles of Uranus and Neptune, all of them sitting on that same imaginary table. Their chalk circles never leave the surface, never tilt, never dive. From above, it looks like clockwork. From the side, it looks like a coin. Because here's what nobody tells you. Almost every poster, every classroom mobile, every slick animation repeats the same word to your brain without saying it out loud. Flat. The solar system is flat. The orbits are flat. The whole thing is a thin disk with almost nothing above or below. And after a few years of seeing that, you stop questioning it. Of course, the edge of the solar system must be the edge of that disk, right? So, let's start at the very beginning of how you were shown the outer regions. We tack on Pluto, still in a ring, a little marble on a slightly more stretched chalk circle. Then we puff that ring out just a bit and call it the Kuiper Belt. Maybe we sprinkle in a few extra dwarf planets. Eris, Haumea, Make. But even then, the whole thing still hugs that tabletop. It's a thicker coin, not a sphere. A DVD instead of a needle-thin CD, but still something you could slide into a sleeve. In that picture, if you flew up out of the screen, what would you see? Almost nothing. Just empty space above and below the plane, as if the solar system simply stops once you leave the disk. And yet, something is above the planets. Something is below them. In the next section, we're going to start bending that tabletop, tilting those chalk circles, and then finally breaking free of the disk altogether. So let's stay with that picture for a moment. The neat, flat clockwork of orbits, the thin disk where everything important seems to live. You know the one. The thing is, it isn't exactly wrong. It's just telling a very edited version of the story. The planets really do mostly share a common plane. They really did form in a flat rotating disk, so their orbits hug that sheet of space we call the ecliptic. If all you care about is where Mars will be next July, that diagram's your best friend. On that level, it works. It's the solar system as seen by a very practical, slightly two-dimensional accountant. Because here's what nobody tells you. To squeeze a three-dimensional, lumpy, chaotic system onto a textbook page, we crush it down into 2 dimensions. We erase the up and down. We draw orbits as chalk circles on a board instead of tilted rings in space. And your brain quietly accepts the trade. After the 10th time you've seen that flat layout, you stop remembering that it was ever a simplification. So imagine this. You're sitting in a spaceship at Earth's orbit, staring at that diagram on your display. The sun in the middle, the planets strung out like beads on a wire. Now you grab the controls and fire the engine straight up, out of the plane of the screen. What do you expect to find? If you trust the picture, you're heading into nothing. Just empty, irrelevant space above and below the disk. That's the hidden assumption the diagram quietly slips into your head. That the solar system is a kind of cosmic vinyl record, and everything that matters is in the grooves. Above and below the plane. Background. Margin. White space. At most, you might imagine a few stray asteroids, but certainly not anything that would redefine where the solar system really ends. And yet something is above the planets. Something is below them. Long-period comets do not care about your flat diagram. They plunge in from every direction, on orbits tilted 60, 80, even more than 90 degrees to that neat plane. Some come in retrograde, effectively falling down on the solar system from above, then whipping back out below. Where are they coming from? Not from a thin disk, from a cloud. Now let's begin to bend that page in your mind. If you follow those comet paths backward, you don't get a wider and wider disk. You get a shell. A roughly spherical swarm of icy bodies wrapped around the sun from all sides. That's the Oort Cloud, not drawn in your schoolbook, but dominating the solar system's volume and absolutely refusing to fit inside a flat picture. In the next section, we're going to leave the diagram entirely and step into that three-dimensional shell where above and below the solar system suddenly means something very different. So let's actually go there. Not on a diagram this time, but as if you climbed into a ship and pointed it straight up from your backyard. Now let's begin. Engines light. The ground falls away, and in a few minutes, the blue fades to black. You pass the orbit of the International Space Station, then the high loops of navigation satellites, and Earth shrinks into a marble with a thin halo of air. You keep going. No turning to chase the sun, no gentle curve along the ecliptic. Just up. The moon's orbit slides past like a tilted ring, off to the side. You know the one. That familiar line from classroom posters, suddenly revealed as just one track in a three-dimensional construction site. A day ago it felt enormous. Now it's a bracelet you've already stepped over. You keep thrusting. Weeks go by. The entire inner solar system starts to pull into view beneath you, not as a jumble of dots, but as a thin glowing disk. Because here's what nobody tells you. From far above the ecliptic, the clockwork we're used to looks more like a record on a turntable than a model on a table. The sun burns at the center, a white pin of furious light. Around it, the orbits of Mercury, Venus, Earth, and Mars flatten into faint, concentric threads. The planets themselves, tiny beads sliding along those threads. So small you could cover all of them with your thumbnail. Beyond them, the asteroid belt thickens the disk just a little, like static on an old screen. Keep rising. Jupiter, Saturn, Uranus, Neptune all join the picture, their orbits widening the disk until it's a bright, razor-thin coin hanging in the dark. Above and below that coin, though, almost nothing. No glowing grid, no dotted lines, no helpful "you are here" arrow. just black? Does it feel empty to you? Staring off the top and bottom of this planetary plane, does your brain whisper that the solar system simply stops there? Or do you have the sense that the diagram is lying by omission, that there's more structure hiding in the darkness? Because in reality, even out here, high above the orbits, you are still deep inside the sun's gravitational territory. Its gravity doesn't care that you've left the flat picture. You're inside an enormous, invisible volume, a bubble of influence that stretches nearly a couple of light years in every direction, filled with potential worlds too small and too faint for your eyes. And yet something is above the planets. Something is below them. Not just empty space, but a distant, three-dimensional cloud of icy bodies that wraps around you from all sides. There's just one problem. We've never flown there. We've never imaged it directly. So if we can't see those worlds, and we've never visited that cloud, how do we know it's there at all? So tonight, we're going to do something ambitious. We're not just going to say, there's a cloud out there somewhere. We're going to ask what might be the most uncomfortable question in all those textbook diagrams. Where does the solar system actually end? Is it the last planet? The heliopause that Voyager 1 just crossed? The place where the sun's gravity finally lets go? Because here's what nobody tells you. Those are three different boundaries, and they don't all sit in the same neat, flat plane you're used to seeing. So what are we really trying to answer tonight? First, we want to know what exists above and below that familiar planetary sheet. You know the one, the tidy clockwork picture where all the orbits line up like grooves on a record. Second, we want to understand why we can say Voyager has left the heliosphere, and yet we're still very much inside the solar system. How can both of those be true at the same time? To get there, we're going to break this into a three-part mission. Step 1, we'll dissect that flat picture you've seen your whole life. We'll treat it like a map legend. What does the ecliptic plane really mean? How thick is the region where the planets actually orbit? What does above and below even refer to when space has no natural up or down? Step 2, we'll uncover why it looks that way. So let's start at the very beginning. A collapsing cloud of gas, rotation, gravity, the way a spinning, shrinking cloud must flatten into a disk, forcing most of the mass into orbits close to a single plane. We'll walk through how that process sculpts space around the sun, and why asteroids, Kuiper Belt objects, and tilted orbits already stretch far above and below that idealized sheet. Step 3 is where the picture breaks. We'll zoom out until the ecliptic stops being the main character. We'll watch the structured disk of planets dissolve into a distant, three-dimensional shell, the Oort Cloud, thousands to tens of thousands of astronomical units away, nudged by galactic tides and passing stars, wrapped around the sun in every direction. Along the way, we'll need an origin story, a physics walkthrough, and then a galactic context check. How far does the sun's gravitational influence reach compared to the heliopause? Where does the Hill sphere fade into the Milky Way's pull? And why does that mean Voyager 1, at barely over 160 astronomical units, has crossed a wind bubble, not the true edge of home? By the end, the solar system will stop being a flat poster and become a layered, three-dimensional bubble embedded in the galaxy, with you sitting off-center inside it. And the next time you look up at the night sky, you won't just see stars. You'll be able to imagine the invisible cloud above you, below you, and all the way out to the real frontier. Now let's begin. So let's start at the very beginning, not with planets, not with a sun, but with a darkness so deep that night would be an upgrade. Billions of years ago, before there was a solar system to call home, there was just a cold, silent molecular cloud drifting through one of the Milky Way's spiral arms. Picture it stretching for light years, a ghostly fog in space, so thin that if you flew through it in a spaceship, you might not even notice. And yet, this is where everything you know began. What was in that cloud? Mostly hydrogen and helium gas, the simplest elements in the universe. But sprinkled through it were heavier elements and tiny dust grains, forged in earlier generations of stars and blown out by supernovae. Every speck of dust was a tiny time capsule. Carbon, oxygen, silicon, iron, all the ingredients that would one day become rocks, oceans, and you. At first, nothing dramatic is happening. Gravity is pulling, very gently, trying to draw the cloud inward. Thermal pressure from the gas is pushing back out. Turbulence ripples through the cloud, stirring and mixing it. For millions of years, these forces nearly balance, and the whole thing hangs in a kind of uneasy truce, not quite collapsing, not quite dispersing, just waiting. Because here's what nobody tells you. The story of why our solar system looks flat starts long before there's any disk at all. It starts here, in this fragile equilibrium, where the slightest nudge can change everything. So what breaks the peace? A shockwave from a nearby supernova could sweep through, compressing part of the cloud. Or the cloud could collide and merge with another passing cloud, like two slow-motion waves crossing in deep water. Either way, that gentle balance snaps. Regions inside the cloud become just dense enough that gravity gets the upper hand and begins to pull them inward. As those patches start to collapse, they don't fall straight down into a point. They can't. Even if the original cloud was turning only once every few million years, it still had a tiny bit of rotation and a bit of asymmetry. And when gravity pulls material inward, that small spin gets amplified, like an ice skater pulling in their arms. Now let's begin to see why this matters. As the collapsing region spins faster, it naturally flattens into a disk, with most of the material orbiting in a single broad plane, and only a little piling up above and below. The future sun will ignite in the center, but the future planets will grow inside that rotating disk. And yet, something is above the planets. Something is below them. Those early tiny deviations, those slight tilts and uneven clumps inside the cloud, are the seeds of a solar system that will be thin and flat in one direction, but stretched and extended in others. In the next step, we'll watch that collapsing cloud turn into the protoplanetary disk that sets the plane for everything that follows. So now we take that lumpy, collapsing cloud and ask a simple question. If gravity is pulling everything straight inward, why doesn't it just fall into a perfect sphere? Why does it turn into a disk instead? Because here's what nobody tells you. The moment you pick out the small region of the molecular cloud that will become our solar system, you've already chosen a special little world, a molecular cloud core. It's just a denser patch inside a larger cloud, a few light years across, with slightly more gravity, slightly more mass, and crucially, a tiny bit of spin. That spin is everything. Even if the core is barely rotating at first, conservation of angular momentum means that as it shrinks, it has to spin faster. You've seen the ice skater version of this. Arms out, slow turn, arms pulled in, suddenly they whip around. Okay, same physics. Our cloud fragment pulls its arms in, and the rotation speeds up. So Let's start at the very beginning of the structure we know. As the core collapses, material falls inward, the center heats up, and a dense, hot ball forms. That's the protostar, the baby sun. Around it, the infalling gas and dust can't just plunge straight in, because they're carrying that angular momentum. Instead, they settle into orbits, forming a broad, rotating band of material called a protoplanetary disk. Now, why a disk and not a fuzzy, rotating blob? Picture countless tiny grains of dust and molecules of gas, all moving on slightly different paths. They collide. They rub past each other. Every collision tends to cancel out motion that's out of the main spin plane more than motion that's along it. If a particle is bobbing above or below, it smacks into others and loses that vertical component, dropping closer to the common plane. Over hundreds of thousands of years, those random up and down motions get ironed out. The result is a flattened, rotating structure, thick in the middle, thin at the edges, like a cosmic pancake. You know the one. This is the solar nebula, stretching several tens of astronomical units across, easily engulfing everything from where Mercury will orbit to far beyond Neptune's future path. In the center, the protostar brightens as more material rains down. Around it, the disk glows in infrared, packed with swirling gas and growing clumps of rock and ice. If you could fly through it, you'd see a hazy golden fog, not a clean, empty plain. And yet, something is above the planets. Something is below them. The planets will form inside this disk, inherit its orientation, and orbit in roughly the same plane. That's the flat picture you've seen in textbooks. But what happens to the material that doesn't stay in that thin sheet? In the next part, we follow the leftovers that get tossed far above and below, toward the realm that will become the Oort Cloud. Those leftovers don't just vanish. They build worlds, and they do it in a way that locks in that flat picture you've had in your head since grade school. So, let's start at the very beginning. In that spinning disk, you've got microscopic dust grains orbiting the young sun, all moving in nearly the same direction, at nearly the same speed. When two grains bump into each other gently, electrostatic forces make them stick. Dust becomes pebbles. Pebbles collide and grow into rocks and boulders. Because here's what nobody tells you. Planets are basically the winners of an ancient, endless, slow-motion traffic pileup. As these boulders get larger, gravity joins the game. Once you're talking kilometer-scale chunks, we call them planetesimals. And now their own gravity pulls in more material. They sweep up pebbles, merge with each other, and grow into planetary embryos. Moon to Mars size bodies, carving lanes in the disk. Most of this action happens right in the mid-plane, where the gas and dust are thickest, so growth is fastest there. That's why the major planets end up in a thin, shared plane. They inherit the geometry of the nursery that built them. But not everything makes it to planet status. Between Mars and Jupiter, the pull of that giant planet keeps material from fully merging. You get the asteroid belt, a debris field of rocky planetesimals, all still mostly confined to the same flattened structure, but never quite assembling into a world. Farther out, beyond Neptune, icy planetesimals and embryos freeze in place as the Kuiper Belt, a broad ring of frozen bodies like Pluto, Eris, and countless smaller objects, all orbiting the sun in that same general disk. Look closer though, and the disk is already fraying at the edges. The orbits of asteroids and Kuiper Belt objects aren't perfectly flat circles. They have inclinations and eccentricities. Some are tilted 10, 20, even 40 degrees off the ecliptic plane. Pluto's 17-degree tilt is a classic example. A few bodies even loop backward on retrograde paths. In other words, the solar system is a disk with thickness, a structure that's being stirred, and that stirring has consequences. As giant planets migrate and tug on these icy leftovers, some get scattered inward to become short-period comets. Others get flung outward on stretched, tilted trajectories that shoot far above and below the original disk. A fraction of those will be nudged just right to stay bound to the sun, but on enormous, elongated orbits. Over hundreds of millions of years, those exiles will puff the flat disk into something else entirely. So what does that look like when a flat ring of debris is inflated into a nearly spherical cloud that reaches almost a light year into space? In the next part, we step outside the planetary plane and meet the true outer architecture of the solar system. When you first step outside that tidy planetary plane, it still looks calm. The major planets are in place. The disk has thinned, and everything seems orderly, almost peaceful. But this is the calm before the gravitational storm. Because here's what nobody tells you. Even after the big planets finish forming, the early solar system is still crowded. Between and beyond their orbits, there's a vast haze of leftover planetesimals and icy bodies, chunks from a few meters across up to dwarf planet scale, all circling the sun in that same broad, flat picture you've seen 1,000 times. To you, it would look like traffic on a cosmic ring road, busy but predictable. Now let's begin to ruin that sense of order. Sitting inside this disk are the giant planets, and they are not polite neighbors. Jupiter and Saturn especially are gravitational bullies. Each one is massive enough that when a small icy body wanders just a little too close, the local flat plane stops mattering, and the rules of the game change. In a close pass, Jupiter's gravity can yank an object's orbit into a new shape in a single encounter. What happens next depends on timing and geometry. Some unlucky bodies get kicked inward, sent on plunging paths that cross the orbits of Mars, Earth, and Venus, where they either collide or get torn apart. Others get flung outward so fast that they escape the sun entirely, ejected into interstellar space as tiny, frozen castaways. And some are put on extremely elongated orbits, long, thin ellipses that climb far above and below the original plane, tilted at steep angles that would make Pluto look conservative. Over tens of millions of years, this doesn't happen once or twice. It happens millions of times. Every close pass, every near miss, every three-body tug with Jupiter and Saturn and the Sun turns the disk into a gravitational pinball machine. You know the one. Launch a ball, watch it ricochet off bumpers, never quite sure where it will end up. Except here the table is the whole solar system, and the balls are icy worlds being scattered in all directions. Slowly, the neat ring frays. The vertical thickness grows. Objects are launched onto orbits that soar thousands, then tens of thousands of astronomical units from the sun before falling back. Some are lost forever, some rain back in as comets, and some settle into distant stable paths. So here's the question. The ones that don't escape into the galaxy, that survive this long, violent game of celestial pinball, where do they actually end up? And yet, something is above the planets. Something is below them. Over billions of years, all those tilted, elongated orbits trace out a shape in space. In the next part, we'll see what that shape is and why it turns our flat solar system into a vast, invisible cloud. That shape is not a neat ring. It's a ghostly shell, and it starts with the planets themselves quietly loading the launcher for billions of years. Now let's begin with those icy leftovers beyond the giant planets. Picture a young solar system. Jupiter, Saturn, Uranus, Neptune, all plowing through a crowded, icy disk. Every close pass, every near miss, gives a tiny gravitational nudge. A little extra speed here, a slight tilt there. Over and over, those nudges pump up the eccentricities and inclinations of countless small bodies until their orbits are anything but calm and flat. Because here's what nobody tells you. The Oort Cloud doesn't appear out of nowhere at the edge of space. It's manufactured, one chaotic orbit at a time, by the same planets you see on the classroom poster. Some icy planetesimals get pushed inward and destroyed. Some get ejected completely, flung into the galaxy as interstellar refugees. But a special group gets thrown onto extremely elongated paths, with aphelia tens of thousands of astronomical units from the Sun. Imagine an orbit that dives through the planetary region, then soars far above the original disk, then falls back down millions of years later. These are not gentle ellipses. They're stretched almost into lines, looping far above and below the ecliptic plane. You know the one, the flat reference plane that made the solar system look like a tidy clockwork. Out here, that picture breaks. At first, all those stretched orbits still remember where they came from. They're tilted, but they're tilted in related directions, like a messy but recognizable disk. So what turns that into a sphere? The galaxy itself starts to help. Distant tugs from passing stars and the slow, steady pull of the Milky Way's tidal field gently twist and torque those elongated orbits. Not in a day, not in a million years, over hundreds of millions of years. Each encounter is weak, but the orbits are so long and so fragile that even a faint shove can rotate their orientation in space. One comet's path gets twisted a little up, another a little down, another sideways relative to the original plane. Slowly, the memory of the disk is erased. The aphelia spread out into every direction, until the Sun is wrapped in a roughly spherical cloud of distant frozen worlds. So, what you end up with is not a separate structure bolted onto the solar system. It is the solar system, fossilized at the edges. The Oort Cloud is a time capsule of our violent youth, a three-dimensional shell of objects launched by the giant planets and then randomized by the galaxy. The flat planetary system sits buried at the center, like a spinning coin trapped inside a vast, invisible snow globe. And yet, something else is hiding in that picture. How big is this snow globe really, and where does it end? To answer that, we have to ask a weirder question. What is this snow globe actually filled with? Because here's what nobody tells you. The largest structure in the solar system is made of things we have never seen where they actually live. On paper, Oort Cloud objects sound simple. They're thought to be icy planetesimals, frozen building blocks that never quite made it into full-size planets. Imagine comet nuclei by the trillion, mixtures of water ice, frozen gases like methane, carbon monoxide, and ammonia, laced with darker rocky material. Not big, glossy worlds with atmospheres. More like dirty snowballs and blackened icebergs drifting through space, each only a few kilometers across. So where did all of this come from? Now let's begin with the part of the solar system that wasn't flat. In the early disk, there was a distance from the young sun called the snow line. Beyond that line, temperatures dropped low enough for water, carbon dioxide, and other volatiles to condense as solid ice. Out there, in that cold zone, Those ices mixed with rock grains to form countless small bodies. Jupiter and the other giants then played cosmic pinball with them, flinging many out of the planetary plane and into wild, elongated orbits. Some were ejected into interstellar space completely, but a fraction were only half thrown. The sun's gravity still held on, barely, stretching their paths into enormous loops that could reach tens of thousands of astronomical units. Over hundreds of millions of years, passing stars and the gentle tidal pull of the Milky Way tugged on those orbits from every direction, smearing them into a roughly spherical cloud above and below every possible plane you could draw. How do we know any of this is real if we've never imaged an Oort Cloud object in place? You know the one, the long-period comet that suddenly appears on the news, screaming in from some absurd angle, with an orbit that takes tens of thousands or even millions of years to complete. Those comets are our messengers. When they fall inward, they bring their chemistry with them. Spectra of long-period comets show exactly what you'd expect from icy bodies born beyond the snowline. Abundant water, carbon monoxide, carbon dioxide, methane, ammonia, plus organic compounds and dust. Their orbits are tilted every which way, some even retrograde, matching what you'd get from a distant spherical reservoir instead of a flat belt. Each one is a sample return mission delivered by gravity. And yet, something is above the planets. Something is below them. Estimates suggest there could be trillions of these bodies, with a combined mass of several Earths, but the range is embarrassingly uncertain. Because here's what nobody tells you. Almost all of our data is a few thousand comets and a lot of orbital backtracking. So the Oort Cloud, as we talk about it, is a statistical ghost, a model, a best fit explanation for the strange comets that dive towards the sun, whispering that far beyond the last planet, the dark is crowded. In the next part, we push past composition and ask a more unsettling question. Just how big is this invisible crowd, and where does the sun's rule finally end? So if the Oort Cloud is a statistical ghost, how do we hunt a ghost we can't see? We do it the way astronomers always have when the universe refuses to pose for a photograph. We watch what moves. The giveaway is a very particular kind of visitor, long-period comets. These are not the regulars, looping around every few decades like Halley. These are the drifters that take tens of thousands, even millions of years to complete a single orbit around the sun. When they finally fall inward, they don't politely follow the planetary traffic lane. They come in at wild angles. Some skim just above the ecliptic plane. Some dive in from far above or below the solar system. Some don't just tilt. They're retrograde, literally orbiting backward. Because here's what nobody tells you. If all your comets were born in a flat disk like the Kuiper Belt, you'd expect most of them to respect that disk. Their orbits might be stretched, their periods long, but their paths would still cluster near the same plane the planets use. That's not what we see. When we map long-period comets on the sky, the directions are almost isotropic. They come from everywhere, north of the ecliptic, south of it, from behind the sun and from above your head at midnight. So let's start at the very beginning of this idea. In 1950, Dutch astronomer Jan Oort looked at the orbits of these long-period comets and noticed two crucial patterns. First, their aphelia, the farthest points in their orbits, tended to pile up at extremely large distances, tens of thousands of astronomical units from the sun. Second, their inclinations were all over the place, including those retrograde paths that no neat, flat belt could easily produce. From that, he made a leap. If comets arrive from every direction with aphelia clustered far, far out, the simplest picture is not a disk at all. It's a roughly spherical cloud of icy bodies surrounding the solar system, extending from a few thousand AU to perhaps 100,000 AU or more. You know the one, the invisible shell that bears his name. Over the decades, as we've cataloged more long-period comets, the statistics have only sharpened that picture. The way their orbits are distributed in inclination, the way their aphelia stretch outward, the way a gentle nudge from passing stars or the Milky Way's gravity can send one toward the inner solar system. All of it points to a vast, extended cloud, rather than a thin ring. And yet something is above the planets. Something is below them. If that cloud is so enormous and so sparse that we've never seen a single member at rest, where does it actually end? Does the outer edge of the Oort Cloud mark the edge of the solar system? Or is there another, deeper boundary where the sun finally lets go? That's where we're heading next. So if the Oort Cloud doesn't give us a clean edge, what does? When does the solar system actually stop being ours and start being out there? To answer that, we have to talk about a different kind of boundary. Not a cloud of icy worlds, but a bubble in plasma. Now let's begin with the part of the solar system that really is shaped like a bubble, the heliosphere. You can picture it as a vast, teardrop-shaped cavity in space, carved out by the solar wind, a stream of charged particles constantly blasting outward from the sun. Close in, that wind is fast and supersonic. It doesn't care about the thin gas between the stars. But as it pushes outward, it rams into the interstellar medium, and there's a point where it can't just barrel through anymore. Because here's what nobody tells you. There are multiple edges out here. And they don't all mean the same thing. The first one is the termination shock. That's where the solar wind suddenly slows from supersonic to subsonic, like a cosmic sonic boom frozen in place. Farther out, where the slowed wind finally balances the pressure of interstellar gas and magnetic fields, you hit the heliopause. That's the true skin of the heliosphere, the place where the sun's wind is pushed back and the galaxy's environment pushes in. Voyager 1 crossed that heliopause in 2012 at about 121 astronomical units from the sun. Headlines said it had entered interstellar space. And in one sense, that's true. The plasma around it is no longer dominated by the solar wind. It's sampling the local interstellar medium. That's a huge milestone. But does that mean Voyager has left the solar system? Not in the way gravity cares about, because the heliopause is a local weather boundary, not a property line. It tells you where the sun's wind fades, not where the sun's ownership of orbits ends. Long-period comets from tens of thousands of AU away still fall toward the sun. Their paths are still bent by its mass. The Oort Cloud, stretched out into that enormous spherical shell, is still held, barely, inside the sun's gravitational influence. So, how far does that influence reach before the galaxy wins? To talk about the true size of the solar system, we need a different concept, the sun's Hill sphere. This is the region around the sun where its gravity beats the combined tidal pull of the Milky Way. Inside the Hill sphere, objects can, in principle, orbit the sun for billions of years. Outside, the galaxy slowly unhooks them. And yet, something is above the planets. Something is below them. That something is still inside the sun's Hill sphere. In the next part, we'll climb all the way out to that limit and see just how small Voyager's journey really is compared to the sun's full gravitational domain. So if the Hill sphere is the sun's true territory, how big is this invisible kingdom you're living in right now? Bigger than every textbook picture has ever prepared you for. The Hill sphere is, very roughly, the region of space where the sun's gravity still wins the tug of war against the Milky Way and passing stars. Not in the sense that nothing else pulls on you, but in the sense that the sun can still keep objects bound in orbit for billions of years. Because here's what nobody tells you. The real boundary of the solar system isn't where the solar wind stops. It's where the galaxy starts to peel things away. Inside the Hill sphere, an icy body can loop around the sun on a stretched, tilted path and remain a loyal comet for ages. Outside it, those orbits become fragile. The slow tidal pull of the galaxy and the occasional flyby of a wandering star can twist, stretch, and finally unhook those bodies so they drift off into interstellar space. The sun stops being the main character and becomes just another extra in the galactic crowd. So how far does that dominance reach? Estimates put the sun's Hill sphere at roughly 1 to 2 light years in radius. That's around 60 to 120,000 astronomical units. You know the one. 1 AU is the distance from Earth to the sun. The classical Oort cloud probably runs from about 2,000 AU out to maybe 100,000 AU. So the outer Oort cloud is brushing right up against the edge of this Hill sphere, and in some directions it may even sit comfortably inside it. Now compare that to where we've actually been. The heliopause, where the solar wind gives up and the interstellar medium takes over, sits only around 120 AU from the sun. Voyager 1, our furthest spacecraft, is a bit over 160 AU out. That sounds epic in a flat diagram. In the Hill sphere picture, it's a tiny step. Voyager hasn't even reached 1% of the sun's gravitational territory. It's not just inside the Oort cloud. It hasn't even reached the inner edge. So, let's start at the very beginning of this new mental model. The edge of the solar system isn't a sharp wall. It's a fuzzy, gravitational fade-out that stretches almost halfway to the nearest stars. There's no glowing boundary, no cliff. Just a slow handoff from the sun's grip to the galaxy's tides. And yet, something is above the planets. Something is below them. A spherical cloud of worlds suspended inside this Hill sphere. In the next section, we'll dive into that realm itself and see what it means that trillions of unseen objects might be sharing our orbit around the galaxy. So if there's this invisible sphere of worlds above and below the planets, how big is it really? How far does the sun's domain stretch before you're not in the solar system anymore? You're just in raw, galactic space. Now let's begin with the numbers that sound fake until you sit with them. The inner Oort cloud is thought to start around 2,000 astronomical units from the sun, 2,000 times the Earth-Sun distance. The outer Oort cloud, it might extend to 50,000, maybe even 100,000 AU, brushing up against 1.5 light years. That's not a typo. That's the scale of the sun's distant icy halo. To feel this, we have to shrink it. You know the one. The classroom diagram where Neptune is the last little marble at the edge. Neptune orbits at about 30 AU. If the distance from the sun to Neptune were just one big step you could take across a room, the inner edge of the Oort cloud would be more than 60 steps away. The far edge? Thousands of steps. You'd leave the building, walk down the street, and keep going while people wonder why you're measuring the neighborhood in planets. Because here's what nobody tells you. That familiar flat picture with 8 planets is like zooming in on the inner few millimeters of a huge sphere. Almost everything the sun owns by volume is not that tidy disk. It's the dark three-dimensional cloud wrapped around it. Let's bring in a real traveler. Voyager 1 has been flying for nearly 50 years and is sitting at roughly 160 AU from the Sun. That's more than 5 times Neptune's distance. Sounds far, right? But compared to the inner Oort Cloud at 2000 AU, Voyager hasn't even reached 10% of the way to the starting line. It's like driving 5 blocks and claiming you're almost across a continent. Push the thought experiment further. Suppose Voyager kept its current speed, about 17 kilometers per second, and you drew a straight line across the Oort Cloud, say out to 50,000 AU. Crossing that width would take tens of thousands of years. If the cloud really reaches 100,000 AU, you're looking at time spans comparable to the entire history of human civilization just to go from one side of our own backyard to the other. So, let's start at the very beginning of the mental picture we carry. The solar system isn't mostly planets with a decorative comet belt tacked on. By volume, it's almost entirely this remote, spherical cloud of icy bodies extending far above and below the planetary plane, sharing our orbit around the galaxy. In the next section, we'll zoom in on what those worlds might actually be like, and how we can be so sure they're there when we've never seen them directly. So now we've met the Oort Cloud as this enormous, distant population of worlds. But there's a deeper twist hiding in its shape, because when we say it extends far above and below the planetary plane, we're smuggling in an idea that doesn't really exist in space. In space, there is no up, there's no down, there's only a reference. For the solar system, that reference is the ecliptic plane, the average plane of Earth's orbit, and roughly the plane of the other planets. When someone says an asteroid is 30 degrees above the solar system, what they really mean is that its orbit is tilted 30 degrees relative to that invisible sheet defined by Earth's path around the Sun. So, let's start at the very beginning of your mental picture. You've seen that flat side view of the solar system. Sun in the middle, planets in a neat line, maybe a thin ring of asteroids, and the Kuiper Belt. You know the one. In that diagram, above means up on the page, below means down on the page, and it feels like the whole system is a cosmic vinyl record floating in space. Because here's what nobody tells you. That record is only the inner, bright part. The planets and most main belt asteroids really do hug the ecliptic, wobbling just a few degrees above or below it. So from far away, they'd blur into a thin, glowing disk. The Kuiper Belt thickens that disk a bit, adding icy worlds on more tilted paths. But the Oort Cloud does something completely different. Oort Cloud objects don't live in a flat ring. Their orbits are scattered into a roughly spherical shell, surrounding the Sun from every direction. Above, below, sideways. Directions that don't even map cleanly onto your sense of up. If you could back away a light year and look at the solar system, you'd see a bright, razor-thin disk of planets and Kuiper Belt objects embedded inside a huge, faint halo of icy bodies stretching out to tens of thousands of astronomical units. And yet something is above the planets. Something is below them. It's just not a ceiling or a floor. It's this three-dimensional swarm of comets held loosely by the Sun's gravity. How do we know it's a halo and not just a bigger, flatter ring? Long-period comets give it away. They plunge in from all angles, high inclinations, even retrograde orbits that move opposite the planets. You don't get that from a thin disk. You get it from a spherical reservoir. So here's the question. When you imagine leaving the solar system, what are you really picturing? Escaping that bright planetary disk? are actually crossing the dark, surrounding halo that wraps it on all sides. But in the next part, we'll find out what it would take to punch through that halo, and why, even after half a century of flight, our fastest probes are still barely inside the shell. So if the Oort Cloud is this dark halo around the solar system, what's holding that halo in place? And what's trying to tear it away? Because here's what nobody tells you. The farther you go from the sun, the less this is a story about our star. And the more it's a story about the entire Milky Way pulling on it from all sides. Out there, the galaxy itself has a kind of tide. Not a water tide, a gravity tide. The Milky Way's mass tugs a little harder on the side of the sun's realm that's closer to the galactic center, and a little less on the side that's farther away. That difference in pull stretches the sun's extended gravitational field, the same way the moon stretches Earth's oceans. It sounds abstract, but if you're a tiny icy body sitting 50,000 AU above or below the planetary plane, that slow, constant stretch can change everything about your orbit. Those galactic tides are patient. They don't fling objects overnight. They very gently tilt and elongate orbits over tens or hundreds of millions of years until some unlucky chunk of frozen rock finds its path warped just enough that the sun starts to win again and reel it inward. That's one of the main ways we think long-period comets get nudged out of the cloud and dropped into the inner solar system on those wild, highly tilted, or even retrograde paths that ignore the neat, flat picture of the planets entirely. But the galaxy doesn't just pull smoothly from far away. Every so often, a star wanders close. Close on these scales might still mean 1 trillion kilometers or more. But to an object barely bound to the sun, that passing star's gravity is a rude shove. It can kick comets inward as new visitors, or outward, hard enough that they're stripped from the Oort Cloud forever and handed over to interstellar space. At some distance, those external tugs win. The sun's grip weakens with the square of distance, while the background pull of the Milky Way and the random flybys of other stars stay roughly the same. Beyond roughly a light year or so, we hit the edge of the sun's hill sphere, the zone where it can still dominate orbits. Past that, the most distant would-be Oort Cloud members don't really belong to us anymore. And here's the twist: that edge isn't fixed. As the sun orbits the galaxy, it plows through spiral arms, star-forming regions, and patches of higher density where passing stars and galactic tides get stronger. In some eras, the Oort Cloud is shaken more violently. In quieter regions, it's left in relative peace. So the Oort Cloud isn't a static, pristine shell waiting politely at the edge of a flat diagram. It's a dynamic frontier, constantly edited by the Milky Way itself, which raises a bigger question. If our galaxy can sculpt the outer boundary of the sun's domain, what happens when we finally try to cross that boundary on purpose? So when we talk about crossing that boundary, there's one name you're probably already thinking of: Voyager 1, our tiny metal ambassador that feels, in the popular picture, like it has already sailed off the edge of the map. Now let's begin with its actual journey. Launched in 1977, Voyager 1 fell inward toward the sun, then stole momentum from the giants. It skimmed past Jupiter in 1979, threading through that radiation-filled maze of moons, then swung by Saturn in 1980, using its gravity as a slingshot. One more sharp turn, and it was hurled out of the planetary plane, climbing above the flat orbits of the major planets and heading into the dark. On paper, that sounds like escape. You know the one. The triumphant headline that Voyager 1 has left the solar system. Because here's what nobody tells you. What it actually left was the heliosphere, the bubble where the solar wind dominates. Around 2012, at a bit over 120 astronomical units from the Sun, it crossed the heliopause and began swimming through the thin interstellar plasma between the stars. But gravity does not care about that invisible bubble. The Sun's pull at Voyager's distance is weaker, yes, but it still rules the orbit. Today, Voyager 1 is a little over 160 AU away, racing outward at more than 17 kilometers per second, and it is still firmly inside the Sun's gravitational domain. In the true three-dimensional picture of the solar system, it's not gone. It's just on a very long, very stretched-out orbit that will never loop back. Here's the scale breaker. The inner edge of the Oort Cloud is thought to begin around 2000 AU. That means Voyager hasn't even traveled 10% of the way to the start of that distant cloud of icy worlds. The main body of the Oort Cloud, stretching tens of thousands of AU, lies far beyond even that. If Neptune's orbit is your driveway, Voyager has made it to the end of the street. The Oort Cloud is the dark countryside beyond the last street light, where you can't even see the road anymore. So let's start at the very beginning of your mental map. Those textbook diagrams that show the Sun, the planets, maybe Pluto, and a little arrow labeled Voyager 1 out here somewhere. They're lying to your intuition. The spacecraft is not at the edge of the solar system. It's barely past the familiar neighborhoods. In gravitational terms, we're still in the suburbs. Voyager 1 is a brave scout wandering just beyond the cul-de-sac of the planets, nowhere near the true city limits of the Sun's realm. And yet, something is above the planets. Something is below them. That spherical Oort Cloud is still waiting far ahead, which forces us to ask, what would it actually take to send a mission all the way into that dark countryside and beyond? So let's actually do the brutal math. If Voyager 1 is our brave scout in the dark, how long would it take that tiny machine to reach the real edge of the solar system? The Oort Cloud's frontier, and then the far side of that invisible sphere? Voyager 1 is moving at about 17 kilometers per second relative to the Sun. That sounds fast. It is fast. In a single second, it crosses the distance you might drive in 10 minutes. But here's the problem. The distances we're talking about aren't road trip distances. The inner edge of the Oort Cloud is thought to begin around 2,000 astronomical units. Voyager is just over 160 AU from the Sun. So, let's start at the very beginning of that journey. To go from 160 AU to 2,000 AU, Voyager needs to cover roughly 140 AU. 1 AU is about 150 million kilometers. Multiply that by 1,140 and you get a distance so large your calculator starts to look nervous. At 17 kilometers per second, that works out to on the order of 300 to 400 years from now, just to reach the inner Oort Cloud. Because here's what nobody tells you. Even after a human lifetime of flight, Voyager hasn't even finished the prologue. Now stretch your mental picture further. The outer Oort Cloud might extend to 50,000 AU, maybe even 100,000 AU. That's up to about 1.5 or 1.6 light years. From where Voyager is today, reaching 50,000 AU at its current speed would take tens of thousands of years. Pushing all the way to 100,000 AU, you're looking at something like 60,000 years. That's not just beyond your lifetime. That's beyond the lifetime of languages, nations, and probably most of our familiar constellations. Compare those numbers to human history. Recorded civilization, cities, writing, organized states, has been going for, 5,000 or 6,000 years? The time it would take Voyager to cross the Oort Cloud is 10 times longer than the entire span from the first pharaohs to your phone. We think of the probe as ancient space history. In Oort Cloud terms, it has barely taken a single step. Could we do better with future propulsion? Sure. Nuclear electric engines, high-performance ion drives, or giant solar sails might push a probe to 2 or 3 times Voyager speed. Maybe a bit more if we really commit. But even if you cut those travel times by a factor of 5, you're still talking thousands to tens of thousands of years to cross the Oort Cloud. Without some radical breakthrough, fusion drives, antimatter, beamed sails, the solar system's true boundary remains a slow-motion destination. So if physical probes crawl on these timescales, how can we hope to explore a structure that big in anything like a human time frame? To answer that, we have to change how we think about going there at all and look for clues that reach us first. So if physical probes crawl on these timescales, how can we possibly learn anything about a cloud that starts thousands of AU out and fades into the dark? We cheat. We let the Oort Cloud send tiny messengers inward and read their paths like a secret code. Those messengers are long-period comets. You know the one, the dramatic, once-in-a-lifetime visitor with a tail stretching across the sky and an orbit that takes tens of thousands of years to complete. When one of those shows up, we don't just take pretty pictures. We track its orbit with absurd precision. Every night, every tiny shift against the background stars gets folded into a trajectory that tells us where it came from and how far out its aphelion lies. Because here's what nobody tells you. When you measure enough of those orbits, you're not really studying individual comets anymore. You're sampling the shape of an invisible reservoir. A comet that swings in from 30,000 AU on a path tilted 80 degrees above the planetary plane is a probe of that region of space. A different comet with a wildly retrograde orbit and aphelion at 60,000 AU is another probe. Add thousands together, and you start to see the outline of a distant, spherical cloud that no telescope can resolve directly. But astronomers don't stop at drawing curves on the sky. They ask a deeper question. If a distant cloud of icy bodies really surrounds the solar system, how should the galaxy itself tug on it? The Milky Way's gravity creates galactic tides that slowly stretch and squeeze the cloud, while passing stars occasionally give it a kick. So we build models that include those tides and flybys, then ask, how often should comets be nudged inward? At what angles? With what energy? Here's where computers do the traveling we can't. Simulations evolve billions of test particles over billions of years, starting from a primordial disk and letting planets, galactic tides, and stellar encounters sculpt the orbits. When you leave out a distant cloud, you can't reproduce the observed flood of long-period comets. Turn on an Oort Cloud-like shell extending from a few thousand to tens of thousands of AU, and suddenly the synthetic comets match what we see. Even the fine print in those orbits matters. Subtle clustering in comet aphelia, slight preferences for certain distances or directions above and below the ecliptic plane hint at where the inner edge of the cloud sits, how puffed up or lopsided it is, and how many trillions of bodies it might contain. It's like reconstructing a fog bank from the way a few headlights emerge out of it. And yet, something is above the planets. Something is below them. Our current Oort Cloud is a best fit model, not a photograph, so there's still room for surprises. Hidden structure, missing populations, even extra layers, which raises an uncomfortable question for the next part of our journey. If we're this uncertain about the sun's own outskirts, what happens when we pull back to the scale of the galaxy itself? So if the outer Oort cloud might be lumpy, tilted, even torn by the galaxy, what if there's a hidden layer tucked further in, where things are calmer? Not out at a light year, much closer. Closer in Oort cloud sounds like a contradiction, but it isn't. Because here's what nobody tells you. Some models say the Oort cloud isn't just one giant shell. It has an inner heart. Astronomers call it the Hills cloud, and in a typical picture of the solar system, you never even see it. This inner component is thought to begin around 2,000 to 5,000 astronomical units from the Sun, just inside the lower edge of the classical Oort cloud we've been talking about. 2,000 AU already feels huge, so let's anchor it. Neptune orbits at about 30 AU. The Kuiper Belt and scattered disks stretch out to maybe 100, a few hundred AU if you're generous. The Hills cloud would start at 20 times that distance and keep going outward. It's not a thicker Kuiper Belt. It's a completely different population, in both distance and in how its orbits behave in three-dimensional space. Out there, gravity is weak, but not gone. The idea is that the inner Oort cloud is more tightly bound to the Sun than the fragile outer shell. Galactic tides and passing stars can strip objects from the outskirts, but the inner layer hangs on for billions of years. Think of it as the deep frozen warehouse behind the visible comet showroom, a long-term reservoir that quietly feeds the rest of the cloud. Now let's begin to trace how a body in that inner cloud might become the dramatic long-period comet you eventually see on a sky chart. A slight nudge from a passing star or the slow flexing of the Milky Way's gravity can stretch an orbit. Over millions of years, that object can be promoted outward into the classical Oort cloud, where its path becomes even more vulnerable to further perturbations. One more shove, and suddenly its orbit dives inward, slicing across the planetary plane on some wild inclined trajectory. So the comets you see blazing through the inner solar system might be on a multi-step journey. Inner cloud to outer cloud to inner planets. You know the one thing those textbook diagrams never show you, that there's a whole invisible traffic system operating thousands of AU above and below the flat planetary plane, slowly rearranging this reservoir. And yet something is above the planets. Something is below them. If an inner Oort cloud really exists, it might hold far more bodies than the outer shell, including objects hundreds of kilometers across. At that point, are we talking about comets or dwarf planet-scale worlds lurking in the dark? Could future infrared surveys or next-generation telescopes ever pick out the very largest of them, turning this theoretical cloud into a mapped frontier? Hold that question, because to answer it, we have to zoom out again, this time to the scale of the galaxy that's doing the pulling. That galaxy that's doing the pulling isn't just stretching the solar system outward, it's also tugging it up and down. So if we zoom back in and ask our original question again, what actually exists above and below the planetary plane? What do we find there? Because here's what nobody tells you. Above and below the ecliptic aren't empty directions. They're crowded with orbits that have simply refused to stay flat. You have high inclination asteroids in the main belt, tilted 10, 20, 30 degrees off the plane. You have centaurs, those unstable ice rock hybrids between Jupiter and Neptune, on orbits that dive through the planetary region from odd angles like cosmic cross traffic. Push farther out and the picture thickens. Beyond Neptune, scattered disk objects like Eris swing along paths inclined 40 degrees or more, some even retrograde, literally orbiting the wrong way compared to the planets. These are the first hints that the neat disk you grew up with is only the bright spine of a much puffier structure, one that gets thicker the farther you go. And yet, something is above the planets. Something is below them. Long-period comets fall in from every direction, with orbits tilted at 70, 90, even 180 degrees to the ecliptic. They don't care about the planetary plane at all. That's why we think the distant Oort Cloud is not a disk, but a nearly spherical halo, a shell of icy bodies surrounding the Sun from roughly 2,000 to maybe 100,000 astronomical units. So how did we go from a flat Earth disk to a round comet cloud? Galactic tides. Over billions of years, the gravity of the Milky Way's disk and passing stars slowly pump energy into the orbits of distant objects. They stretch them, twist them, and crucially, they tilt them. Orbits that started only slightly off the plane get lifted higher and higher until their directions are almost random. The mass is still concentrated in the inner disk, but the vertical spread keeps growing, turning the outer solar system into a thick fog and finally into that nearly isotropic Oort Cloud. Above and below the plane, you're also leaving the Sun's orderly bubble of plasma. You run into the local interstellar medium, a thin gas threaded with magnetic fields, and a rain of high-energy cosmic rays. The heliosphere itself is tilted with respect to the galactic plane, so its boundary, the heliopause, is like a skewed, wind-blown bubble the Voyagers had to punch through at odd angles. Hold that three-dimensional picture in your mind. A thin, bright disk of planets and belts, wrapped in a vast, dark, spherical halo, reaching a light year above and below. Because now we have to ask an even stranger question. If this is the true shape of the solar system, where does it actually end? So here's the twist. We're asking where the solar system ends, in a universe where end doesn't even point in a particular direction. In space, there is no up, there's no down. There's only this way and that way relative to something you chose as a reference. Because here's what nobody tells you. Every time you see an arrow for north in a space diagram, someone made that up. It's a convention, not a cosmic rule. On Earth, gravity is the tyrant that trains your brain. Down is where your feet go. Up is where you'd fall if gravity suddenly turned off. Your inner ear, your muscles, your whole sense of balance is wired to a planet pulling you toward its center. So when you look at a picture of the solar system, your brain does the same trick. It quietly asks, okay, what's up here? What's down? Textbook artists know this, so they give your brain a hand. They lay the ecliptic plane out as a nice horizontal line, the orbits as flat ellipses, the sun in the middle. Then they label north as the top of the page. You know the one. It feels natural, like we're hovering above a cosmic table looking down at a clockwork model. But that orientation is just a choice. Rotate the whole thing 90 degrees, and suddenly the solar system is vertical. Spin it again, and you're looking along the edge of the planetary plane instead of down on it. Nothing in the physics cares. The planets still orbit. The comets still fall. The Oort Cloud still surrounds us. So why do we cling to that one familiar view? Because once you pick a top and a bottom, your brain starts ranking directions. Above the plane feels like out of bounds. Below the plane feels like the basement. The flat line of the ecliptic becomes the main stage, and everything else turns into background noise. And yet, something is above the planets. Something is below them. Those tilted asteroid orbits, Those high-inclination Kuiper Belt objects? In most diagrams, they get drawn as little arcs poking politely above and below the page, as if they're side characters visiting from the third dimension. The true three-dimensional thickness of the system gets compressed into a tiny visual accent. Now stretch that problem out to the Oort Cloud. In a flat diagram, it often becomes a faint ring or a fuzzy halo around the sun, like a decorative border. But the real picture is a spherical swarm, a three-dimensional shell of icy worlds that looks the same from every angle. Turn the solar system upside down, tilt it, spin it like a basketball in zero-G. The Oort Cloud doesn't care. It just wraps the sun in all directions. So here's the challenge for your brain. Can you let go of top and bottom for a moment and imagine that shell as truly directionless? Because once you do, the next question gets even harder. If every direction is just as real and the Oort Cloud surrounds us on all sides, what does it actually mean to leave it? So if out is suddenly directionless, how do we end up with all those neat, flat solar system diagrams you've seen your whole life? You know the one. The sun on the left, the planets in a tidy line, maybe Pluto hanging out on the edge like it's guarding the door. That picture is not the solar system. It's a map. And like a subway map, it lies to you on purpose. Think about the subway in a big city. The lines are drawn as straight segments. The stations are evenly spaced. North isn't really up. And the river might be a single blue stripe. Nobody uses it to measure how many actual meters it is between stops. You use it because it makes sense of a tangled, three-dimensional mess. Because here's what nobody tells you. Solar system diagrams are doing exactly the same trick. To fit the whole thing on a page or a screen, we flatten it into a single plane and crop it aggressively. We choose the ecliptic plane as our track layout, draw the orbits as thin rings, and then stop the picture at Neptune, or if we're feeling bold, at the Kuiper Belt. Everything beyond that, gone. Not because it isn't real, but because it doesn't fit. What gets lost in that crop is enormous. The Oort Cloud that wraps the sun in all directions from about 2,000 to tens of thousands of astronomical units. Usually erased. The sun's Hill sphere, that huge bubble up to nearly 2 light years, inside which our star's gravity still wins against the Milky Way. Almost never shown, the fact that above and below that pretty planetary plane, the galaxy is stretching, tugging, and occasionally flinking comets in with passing stars. That vertical galactic context is just sliced off. And that editing has consequences. When every picture ends at Neptune, your brain quietly files edge of the solar system right there with the last planet. When Voyager 1 leaves the heliosphere, headlines scream that it's in interstellar space and your intuition cheers because the map in your head says, "We did it. We're out." But in Oort Cloud terms, Voyager is barely off the sidewalk. We underestimate the sun's true domain and overestimate how far we've actually traveled. So here's the pattern interrupt. The problem isn't that the diagrams are wrong. It's that we forget their choices. Every time you see a space picture, you can ask, what did they decide to show and what did they leave out? Did they keep the Oort Cloud, the Hill sphere, the galaxy around us? Now, let's begin treating those images as questions instead of answers. Because once you start reading the omissions as loudly as the labels, the next step is unavoidable. We have to redraw the map of where Voyager really is, and how far we still have to go. So let's actually redraw it. Not on paper this time, but in your head. Now let's begin with a version you already know. You know the one. the neat, flat solar system diagram, with the sun in the middle. The planets on tidy ovals, everything lying in a single plane like a cosmic vinyl record. Hold that picture steady. Mercury, Venus, Earth, Mars. Then the wide gap to Jupiter and Saturn, out through Uranus and Neptune, all orbiting in roughly the same flat slice of space. Push that disk outward in your mind, past Neptune at 30 astronomical units. Sketch in the Kuiper Belt as a thicker, fuzzier ring from about 30 to 50 AU, packed with icy worlds like Pluto and Eris, tilted and stirred, but still mostly clinging to that plane. This is the part every poster shows you. This is the part that tricks you into thinking the solar system is small. Because here's what nobody tells you. That flat picture is just the bright center of a much larger structure. So now, keep the disk, but imagine drawing a transparent bubble around it. At first, it just barely wraps the Kuiper Belt, a few hundred AU across. Then you start to expand it. 1,000 AU, 2,000, 10,000. The disk in the middle shrinks to a thin coin, hanging at the center of an enormous, ghostly sphere. That growing sphere is your first taste of the Oort Cloud. Let it swell until its radius is nearly a light year, maybe 50,000 AU or more. The sun and planets are now a pinprick at the center. The ecliptic plane that felt so important a moment ago is just a razor-thin sheet, slicing through a vast, almost empty ball of space. Now we populate it, not with dense fog, but with lonely grains. Scatter trillions of tiny icy worlds into that sphere, each one a frozen comet nucleus. They are so far apart that, on average, you could fit the entire Earth-Sun distance between neighbors. And yet something is above the planets, something is below them. The cloud ignores the old plane. It wraps around from every direction, held only loosely by the sun's fading gravity. Time for a reality check. Take Voyager 1, our most distant spacecraft. Place it in your mental model, just outside the heliosphere at about 160 AU. Where is it? Still hugging the very center, barely off the sun's doorstep compared to that 100,000 AU sphere around it. On this scale, Voyager hasn't left the city. It has stepped off the porch. Lock this in. The solar system is not just a bright, flat disk. It is a disk floating inside a gigantic, dark, gravitational bubble. This is your new default picture. Because once you see that sphere, the next question is unavoidable. What does it really mean to say we've left the solar system at all? So if our solar system is really this giant dark bubble in space, and the Oort Cloud fills that bubble, you might be wondering something slightly unsettling. If it's that big, could it be hiding whole planets out there that we've never seen? You know the one. The sci-fi image of a lonely Earth-sized world drifting through the cloud, orbiting our sun once every few million years, completely invisible to us. Because here's what nobody tells you. When we say the Oort Cloud might hold trillions of bodies, your brain quietly turns that into a crowded snow globe. It feels like there has to be room for secret worlds between all those icy specks. Now let's begin by breaking that picture. The Oort Cloud is huge in radius, but almost unimaginably empty in density. Those trillions of comet-sized objects are spread through a shell that may run from a couple thousand astronomical units out to nearly 100,000. That's up to 1.5 light years. If you shrank the sun to a grain of sand, the Oort Cloud would be out near the far wall of a stadium, and each icy body would be smaller than dust motes swirling in the rafters. Most of it is just space. So could a planet hide there? In principle, gravity doesn't forbid it. A Mars-sized or even Earth-sized body could orbit at tens of thousands of AU and still be bound to the sun. But gravity also betrays it. A massive planet in the distant solar system would tug on everything else. It would subtly twist the orbits of known planets, Kuiper Belt objects, and long-period comets. Over decades, we'd see patterns that don't quite add up. That's exactly why ideas like Planet 9 exist. Astronomers noticed that some extreme Kuiper Belt objects, tens of billions of kilometers out, have oddly clustered orbits, as if something heavy is shepherding them from far beyond Neptune. The proposed Planet 9 lives not in the far outer Oort Cloud, but in the inner fringe, maybe a few hundred to a few thousand AU away. Close enough that its gravity can sculpt the disk, far enough that it would still be painfully faint. And yet, something is above the planets, something is below them. Infrared sky surveys have already ruled out Jupiter-sized bodies across most of the Oort Cloud. They would glow with leftover heat. Micro-lensing searches can catch massive objects as they drift in front of background stars. The bigger the hidden planet, the harder it is for it to stay hidden. So the most honest answer is this. The Oort Cloud is probably dominated by small, icy fragments, not secret twin Earths. But the door isn't completely closed on larger worlds in that dark shell, which raises a deeper question. If we can't see them directly, how do we read the invisible fingerprints they leave on the solar system shape? Those invisible fingerprints? Sometimes they crash straight through the inner solar system, glowing. One of the best examples flew past Mars in 2014, C2013A1, better known as Siding Spring. You know the one. An icy nucleus only a few kilometers across, dropping in from almost straight above the planetary plane at more than 50 kilometers per second, missing Mars by just about 140,000 kilometers. That's closer than our moon is to Earth. For planetary scientists, that was a near miss from the deep. On paper, its orbit looks almost absurd. A period of roughly 1 million years. A semi-major axis of hundreds of thousands of astronomical units, out near the Sun's Hill sphere, where galactic tides tug as much as our star does. An inclination of about 129 degrees, which means it's not just tilted, it's retrograde, diving through the solar system against the planet's direction of travel. That alone tells you this thing did not grow up in the relatively neat Kuiper Belt. Because here's what nobody tells you. The Kuiper Belt is still a disk. A thick, messy one, but a disk all the same, clustered around the ecliptic. Long-period comets like Siding Spring ignore that geometry completely. Their orbits point almost randomly in space, forming a nearly spherical distribution. That's exactly the fingerprint you'd expect if they're falling in from a vast, isotropic Oort Cloud. A dark halo of icy fragments surrounding the sun from all directions at once. Most of the time, each of those fragments is frozen and invisible, parked tens of thousands of AU above or below the planetary plane in perpetual night. Then some distant nudge, another star, the gravity of the Milky Way itself, tilts its orbit just enough. The object begins a slow million-year plunge inward. For nearly all of that journey, nothing happens. No tail, no drama, just a cold pebble in the dark. Cross a certain line, though, and the sun wakes it up. As Siding Spring rushed inside the orbit of Jupiter, sunlight started cooking its ices. They sublimated straight into gas, dragging dust with them, building a glowing coma and a tail millions of kilometers long. From far away, it looked like a tiny star growing a ghostly streamer. Up close, orbiters around Mars were literally sandblasted by microscopic grains, from a visitor that spends almost its entire life beyond our maps. Now let's begin to see why these apparitions matter. Every time a long-period comet swings through, it delivers a sample from the Oort Cloud straight into the inner solar system. Its orbit encodes where in that halo it came from. Its composition, carbon monoxide, carbon dioxide, exotic organics, records the temperature and chemistry of the sun's birth environment. We haven't flown a probe to 50,000 AU, but by reading these icy time capsules, we're already doing fieldwork in the Oort Cloud without ever leaving home. And yet, something is above the planets. Something is below them. The question is, how do those distant tides and flybys actually sculpt this invisible comet reservoir over billions of years? Those distant tides and flybys don't just sculpt a pretty halo for our solar system. They can turn into a loaded slingshot aimed at the inner planets. Because here's what nobody tells you. When the galactic tide flexes, or a passing star brushes the edge of the sun's gravity, it's not just orbit shapes that change. Entire swarms of Oort Cloud objects can be nudged, ever so slightly, onto long, plunging paths that dive straight through the flat planetary plane. One perturbation and out there, a million icy bullets in here. Now let's begin with the basic picture. The Oort Cloud is weakly bound. A tiny change in gravity at 50,000 AU can tilt an orbit by degrees, turn a lazy circle into a razor-thin ellipse. Over millions of years, those tiny changes add up to comet showers. Waves of long-period comets falling toward the sun from above, below, and every angle. You know the one place they all have to cross, the region where we keep all our planets. So could that matter for life on Earth? There's a hypothesis that when the sun bobs up and down through the Milky Way's disk, the changing galactic tide periodically stirs the Oort Cloud. Some researchers have tried to match those vertical oscillations to spikes in impact craters, and even to mass extinctions in the fossil record. The idea is simple and terrifying. Every so often, the galaxy itself leans on our comet reservoir and sends a storm towards the inner solar system. If just one of those long-period comets hits, the energy is obscene. These objects can be tens of kilometers across, coming in at 50, 60, even 70 kilometers per second relative to Earth. A single impact could release more energy than the entire global nuclear arsenal by orders of magnitude. Oceans boil locally, rock vaporizes, the sky fills with dust and aerosols. You get climate whiplash, acid rain, ecological collapse. Not a great day for complex organisms. And yet, something is above the planets. Something is below them. It's not just empty space, it's a three-dimensional minefield of potential impactors waiting for the right gravitational nudge. Over geological timescales, that invisible shell may quietly decide which worlds stay habitable and which get reset. But here's the catch. The evidence for neat, clock-like comet showers is messy. Crater ages are uncertain. Extinction timelines are noisy. Some studies see a pattern, others don't. Asteroids in the inner solar system still dominate the known impact risk on human timescales. They're closer, easier to perturb, and we've already been hit by them in recorded history. So the Oort Cloud is not the thing that should keep you up tonight. It's the thing that should haunt your sense of deep time. Because once you zoom out to tens or hundreds of millions of years, that faint spherical cloud stops being a curiosity and starts being part of the life support system for planets like Earth. The real twist is what this means for our future, and for any civilization that wants to survive its own cosmic neighborhood. To see that, we have to ask a harder question. If the Oort Cloud can threaten us, Could we ever learn to reach out and touch it first? So if we want to touch it first, we have to do something slightly insane. We have to design a mission whose destination is not a planet, not a moon, but a faint statistical cloud, a light year away. How do you even aim it to something you've never seen directly? Because here's what nobody tells you. An Oort Cloud mission breaks almost every quiet assumption we make about space probes. The distances are brutal. Voyager 1 has been flying for nearly 50 years, and it's only at about 160 astronomical units. The inner Oort Cloud doesn't really start until something like 2000 AU. At Voyager speeds, you're talking tens of thousands of years just to reach the lobby. So the first design meeting hits a wall: travel time. At current chemical rocket velocities, a mission duration is longer than recorded human history. Power is next. Out there, sunlight is so weak that solar panels are basically decorative. RTGs like Voyagers decay over decades, not millennia. Then communication taps you on the shoulder. A probe a light year out has a round-trip signal time of about 3 years. You send a command. You wait. You grow old. You get the idea. Now let's begin to cheat. If we want to cross that gulf in something like a human time scale, we need propulsion that sounds more science fiction than engineering memo. Nuclear electric propulsion, with reactors driving high-efficiency ion engines, could slowly spiral a probe up to tens of kilometers per second beyond what rockets alone can do. Fusion concepts promise even higher exhaust velocities. If we can ever make a fusion device that's more power plant than experimental art project. Or you go stranger. Beam sails, a feather-light reflective sheet, shoved outward by a giant laser or microwave array in the inner solar system, riding a column of light until it coasts into the dark. Stage gravitational assists that dive past Jupiter, Saturn, even the Sun itself on a razor-thin trajectory, trading peril for exit speed. You know the one, the kind of orbit diagram that makes mission planners sweat. So, what would this mission actually do? Imagine a probe launched towards the outer solar system, threading a series of assists, then lining up with the inbound path of a known long-period comet, or an object inferred from its tug on that comet's orbit. It flies through the region where those bodies spend most of their lives, not just their brief, dramatic visit near the sun. The science wish list is wild. In situ dust detectors mapping how dense the cloud really is above and below the planetary plane. Tiny impactors or harpoons sampling pristine ices that have been in deep freeze since the solar system was born. Instruments tracing the local magnetic field, watching how the sun's gravity and the Milky Way's tides wrestle over each icy fragment. And yet something is above the planets. Something is below them. A true Oort Cloud mission is beyond us right now, but designing it forces us to face the real scale of our neighborhood and the radical innovations it demands. The real question is not just how we'd build that probe, but what kind of civilization we'd have to become before launching it would even make sense. So here's the uncomfortable truth hiding in that picture we've been building. Even our bravest machines have barely stepped off the front porch. Voyager 1 has been flying for nearly 50 years, half a century of continuous motion. It's about 160 astronomical units from the sun right now, out past the planets, out past the Kuiper Belt, out in what headlines called interstellar space. And yet, in terms of the Oort Cloud, it hasn't even reached the lobby. Because here's what nobody tells you. 160 AU is still a tiny sliver compared to an outer boundary that might sit at 50,000 or even 100,000 AU. So, let's start at the very beginning of our mental map. You know the one. The flat solar system diagram with the neat rings for Mercury, Venus, Earth, all the way out to Neptune, and maybe a dotted circle for Pluto if the artist is feeling nostalgic. We added the Kuiper Belt, we added scattered icy worlds, and we told ourselves, okay, that's the edge. But the inner Oort Cloud is expected to begin a couple thousand AU out. Voyager isn't even a tenth of the way to that inner edge, let alone to the true outskirts. On human scales, what we've done is staggering. We've flown past every major planet. We've mapped moons, rings, storms, and magnetic fields. New horizons threaded the needle past Pluto and kept going. In the flat picture, it feels like we've swept the board. But zoom out to the sun's full gravitational halo, and those missions are still hugging the city center, while the suburbs, the countryside, and the wilderness beyond the last streetlight remain untouched. This is where the language gets sneaky. When you hear that Voyager has left the solar system, that's technically about the heliosphere, the bubble carved out by the solar wind. It crossed the heliopause, where the sun's charged particles give way to the interstellar medium. Important milestone. Big deal for plasma physics. But gravity does not stop there. The sun's Hill sphere, its true gravitational territory, stretches roughly a light year or more in every direction. By that measure, Voyager is still deep inside the sun's domain. So what does that make us? In galactic terms, we haven't left our home city. We haven't even crossed the city limit sign. We're like explorers who have meticulously mapped the downtown streets, drawn beautiful diagrams of every intersection, and then quietly ignored the fact that 99% of the map is still blank. And yet something is above the planets. Something is below them. A spherical cloud of dark, frozen worlds that our probes have never seen. What does it really mean to say we understand our solar system, when most of our own star's neighborhood is still invisible, unexplored, and only inferred from the rare visitors that fall inward? Because once you feel that gap, a new question appears. What kind of exploration counts as knowing where we live at all? So if most of our own star's neighborhood is invisible to us, what does our neighborhood look like from the outside? Not just from above the solar system's plane, but from outside the entire system of planets, comets, and clouds. Now let's begin to zoom out for real. Imagine taking that whole Oort Cloud bubble, the planets, the Kuiper Belt, every orbit we've talked about, and shrinking it down until the outer edge is smaller than a grain of sand. On that scale, the Milky Way becomes the room you're standing in. A flattened, glowing disk of stars, gas, and dust about 100,000 light years across, and only a few thousand light years thick. It's like a cosmic vinyl record, absurdly wide compared to its thickness. We live inside that record, not in the center, not out on the very edge, but about 26,000 light years from the galactic core, tucked into one of the spiral arms. Our sun orbits the galaxy once every 225 to 250 million years. One galactic year. Dinosaurs lived, evolved, and vanished in less than a single lap of that orbit. You know the one. The textbook picture with a little yellow dot halfway out on a spiral arm. That's actually pretty close. But because here's what nobody tells you. Even that top-down galaxy picture hides a plane. The Milky Way has its own midplane, defined by the average orbits of hundreds of billions of stars. That's the galaxy's version of the ecliptic, and our solar system doesn't line up with it. The ecliptic plane is tilted by roughly 60 degrees relative to the galactic plane, so are above and below for the planets sliced diagonally through the galaxy's own up and down. When you say an asteroid is above the solar system, you're really saying it's above the ecliptic, not hovering over the Milky Way's disk like some cinematic establishing shot. Our local flat picture is twisted inside a much larger flat picture. And yet, something is above the planets. Something is below them. The Oort Cloud doesn't care about the ecliptic. It's roughly spherical, a tiny frozen bubble embedded in the much larger galactic disk and halo. Even if it stretches a light year or more from the sun, that's microscopic compared to the galaxy. Our entire cloud is just one grain of dust drifting in a beam of starlight. That's our real three-dimensional address. Not just in the solar system, but tilted at a particular angle, moving through the Milky Way's gravitational field, riding the galaxy's tide. So what happens when that vast galactic environment starts tugging on our little bubble of comets and worlds above and below the plane? It doesn't just tug, it rocks us. As the sun orbits the Milky Way, it doesn't trace a perfect circle in a flat, calm lane of space. It bobs, up and down through the galaxy's midplane, like a ship riding the long, slow swells on a dark ocean. Because here's what nobody tells you. Our entire Oort Cloud is surfing those waves with us. So let's start at the very beginning of that motion. The sun takes about 230 million years to go once around the galactic center. But layered on top of that huge orbit is a gentle vertical oscillation. Every few tens of millions of years, we drift above the Milky Way's thin disk, then fall back through the galactic plane, then overshoot below it and repeat. To you and me, that sounds abstract. To a barely bound comet 50,000 AU out, it's life or death. Near the galactic plane, the density of stars, gas, and dark matter is higher. That means the large-scale gravitational field is stronger and more sharply curved. The result is what astronomers call the galactic tide. A slow, persistent stretching force that tugs more on the far side of the Oort Cloud than the near side. When the sun plunges through denser regions, that tide gets a little stronger, and orbits that were almost perfectly balanced can be nudged just enough to fail. Picture a comet in the outer cloud, lazily circling once every hundreds of millions of years. A tiny extra pull from the galactic tide tilts its path, shrinks its closest approach to the sun, and suddenly it's not a quiet ice world in the dark anymore. It's a long-period comet on a steep, plunging orbit that can dive straight through the inner solar system from far above or below the planetary plane. You know the one. The kind of orbit that ignores the neat, flat picture in your textbook. Now let's begin to mess with your sense of deep time. Some researchers have tried to link these vertical oscillations through the galactic plane to periodic spikes in impact craters on Earth, or even to mass extinctions. The idea is tempting. Every time we cross the disk, the galactic tide stirs the Oort Cloud, rains more comets inward, and bad days follow for dinosaurs. It's a great story. The problem is the evidence is messy, the timing is fuzzy, and no strict cosmic metronome has survived careful statistical checks. Now, what does survive is the bigger lesson. The Oort Cloud isn't a frozen, eternal shell. It's being constantly compressed along one axis, stretched along another, and slowly eroded as the sun moves through different neighborhoods of the galaxy. Passing stars tweak its edges. Molecular clouds can jostle entire swaths of it. Galactic tides quietly reshape its overall halo. And yet, something is above the planets. Something is below them. It's this vast, invisible cloud, endlessly molded by a galaxy we're sailing through, not sitting inside like a framed diagram. Our solar system isn't an isolated island. It's a ship in a changing sea. So what happens when another ship, a passing star, cuts right across our wake? When that passing star cuts across our wake, it doesn't hit a hard wall. It brushes past a blur of borders, because here's what nobody tells you. Our edge of the solar system changes depending on what kind of edge you care about. So, let's start at the very beginning of those edges we've been quietly stacking. Closest in, you've got the familiar planetary region, the orbits of the 8 major planets, all hugging that mostly flat ecliptic plane. You know, the one from every textbook picture. Step out a bit farther and you hit the Kuiper Belt, a thicker, colder donut of icy worlds past Neptune. That's one kind of boundary, where big planets end and small frozen debris takes over. Keep going, and the sun throws up another border, the heliopause. That's where the solar wind's magnetic bubble finally loses its fight against the galaxy's charged particles. Voyager 1 crossed that line around 120 astronomical units out. In one sense, that's where we entered interstellar space. But did we actually leave the solar system there? Not if you care about gravity. Because beyond the heliopause, the Oort Cloud still hangs in the dark, from a couple thousand AU to maybe 100,000 AU or more, a nearly spherical cloud of icy bodies that still orbit our sun. That's a different frontier, where the sun's material leftovers thin out into a halo of almost nothing. And beyond even that, there's the sun's Hill sphere, stretching roughly 1 to 2 light years. Inside that region, the sun's gravity still wins a tug of war against nearby stars. Outside it, comets are more loyal to the galaxy than to us. If you pick this as your border, then we haven't left the solar system at all. We haven't even reached the fence line. So which edge is the real one? The magnetic edge at the heliopause? The material edge at the outer Oort Cloud? Or the gravitational edge at the Hill sphere? The answer is yes, all of them. Because in a universe without hard walls, borders aren't lines, they're gradients, where influence fades with distance instead of snapping off. Now let's begin to think less in terms of sharp circles on a diagram, and more in overlapping spheres of influence. The sun has its bubble. The galaxy has its own tidal reach. The local group of galaxies stretches that influence even farther. You're not in one box. You're nested in layers. What happens to exploration, ownership, and even the idea of home when every here is inside a larger here? If a probe crosses the heliopause but is still in the Oort Cloud, have we left home or just stepped onto the porch? And when our descendants finally cross the sun's Hill sphere, will that feel like leaving the solar system, or leaving the galaxy's quiet backwater for an even stranger sea? Because the next question is brutal. If borders are gradients, how do you ever know you've truly left? So to answer that brutal question, we have to do something uncomfortable. We have to delete the picture in your head. You know the one. The tidy flat solar system diagram from school. Sun on the left. Little circular orbits marching outward, maybe ending at Neptune, maybe at Pluto, maybe with a polite label that says Kuiper Belt. And then, vague emptiness. Beyond that, the universe. Full stop. That picture was useful. It taught you the order of the planets. It hinted at the ecliptic plane. It made gravity feel like clockwork. But it also planted a quiet lie, that the solar system is a thin disk with a sharp outer edge. And once you pass the last planet, you're basically in deep interstellar space. Because here's what nobody tells you. That flat disk, It's just the bright inner floor of a much larger three-dimensional bubble. In the new mental model, the planetary orbits and the Kuiper Belt are a glowing, razor-thin record at the center, maybe 30 or 50 astronomical units across, slightly thickened by inclined orbits and scattered objects. Around that record, enveloping it in all directions, above the plane, below the plane, is the Oort Cloud, a vast spherical halo of icy bodies stretching from a few thousand AU out to tens of thousands, nearly a light year. So the solar system isn't a plate. It's a layered snow globe, a thin, bright disk floating inside a dark, almost empty sphere that holds most of the system's volume. When a long-period comet dives in from a random direction, on a path tilted 60 degrees or even retrograde to the planets, that's the sphere announcing itself. Now drop Voyager 1 into this picture. After nearly 50 years of flight, it's a bit over 160 AU from the Sun. That sounds huge. But compared to an Oort cloud that might reach 100,000 AU, Voyager has barely stepped off the inner carpet. It has crossed the heliopause, yes, but it is still deep inside the Sun's gravitational territory, nowhere near the edge of the Hill sphere where galactic tides start to win. And those galactic tides matter. The Milky Way's gravity, plus passing stars, constantly tug on the outer Oort cloud, stretching it, squashing it, knocking comets loose. The edge of the solar system is not a clean shell. It's a fuzzy, shifting frontier where the galaxy and the sun negotiate custody of every icy grain. So here's the upgrade. From now on, when you hear solar system, don't see a flat classroom poster. See a multi-layered bubble, inner rocky worlds, outer giants, Kuiper Belt Taurus, and then that enormous dim cloud in all directions. And yet, something is above the planets. Something is below them. So how do you actually picture up and down inside a spherical halo that lives inside a spinning galaxy? So here's the twist. We keep saying above and below the solar system. But in space, there is no universal up. There is no universal down. There is only a plane you chose and the directions you measure away from it. For us, that starter plane is the ecliptic. You know the one. The flat sheet defined by Earth's orbit that textbooks quietly promote to the plane of the solar system. When we said asteroids sit above or below the planets, what we really meant was that their orbits are tilted relative to this ecliptic plane. Because here's what nobody tells you. Even that plane is already tilted. The whole solar system disk is cocked about 60 degrees relative to the Milky Way's galactic plane. So if some galactic cartographer looked at us, their version of above and below would slice our picture at a completely different angle. Let's do a quick mental experiment. Hold the solar system in your mind as a flat dinner plate of orbits, with the Oort cloud as a huge, faint bubble around it. Now slowly rotate the entire scene until that plate is vertical, like a frisbee balanced on its edge. What used to be above the planets is now to the left. What used to be below is now to the right. Did the Oort cloud change shape? Of course not. That spherical halo does not care which way you tilt your imaginary camera. So if up and down are negotiable, is there any direction that is actually special? There is one. Toward the sun versus away from the sun. That's the real cosmic compass here, because gravity writes the rules in that language. If an object's path curves enough toward the sun, it's bound. Its orbit closes on itself, and it belongs to the solar system. If its path points too far away, with too much speed, the trajectory opens and it escapes, joining interstellar space for good. This is how navigators think. Mission planners don't draw flat circles. They work with full three-dimensional orbits, with inclinations, ascending nodes, arguments of perihelion. When Voyager 1 left the planetary region, it didn't politely follow the ecliptic like a train on a track. Its path is tilted, arcing above that classroom diagram, carving its own lane through the sun's gravity field. Now project that forward. Future starships won't go up out of the solar system like leaving a page. They'll aim along arbitrary paths through this 3D halo, picking departure directions that exploit the sun's motion around the galaxy, threading between Oort Cloud comets, sliding out along whatever line in space makes the journey easiest. The question won't be, are we going above or below? It will be, how are we spiraling away from the sun, and into which part of the galaxy are we falling next? Because once you see direction this way, the next question gets much stranger. Where does the sun's pull actually stop? The honest answer is, we're not sure where the sun's pull really stops. Not in detail. We have rough numbers, big spheres on a diagram, but when you zoom in, the edges of our own backyard blur into guesswork. Because here's what nobody tells you. The Oort Cloud, this gigantic shell we keep talking about, is mostly an equation, not an observation. We think the inner edge starts somewhere around 2,000 or 3,000 astronomical units. The outer edge? Maybe 50,000, maybe 100,000. That's a factor of 2 uncertainty on the literal size of the solar system. How often do you see that in a textbook picture? We don't know the total mass either. Is it a few Earths' worth of ice and rock, or a few dozen? That difference changes how violently the early planets must have scattered debris outward, how strong the sun's gravity had to be to hold on, and how easily the galaxy can shake those orbits loose. And inside that mass, what's the size distribution? Are there mostly sand-grained pebbles with a sprinkling of comets, or trillions of 10-kilometer worlds with a secret population of objects hundreds of kilometers across? You know the one question that keeps dynamical astronomers awake? Are there bigger bodies out there? Not just comets, but dwarf planets, even something approaching a Mars or Earth in the deep dark. The whole Planet 9 debate lives right on this fault line. Is there a hidden world, tens of billions of kilometers away, shaping the orbits of distant Kuiper Belt objects? Or are we just seeing patterns in a tiny, biased sample? Now let's begin to appreciate how blind we are. An Oort Cloud object is incredibly faint, incredibly slow, and surrounded by a dense background of stars. From here, it hardly moves against the sky. It doesn't flare. It doesn't shout. It just sits there, lost in the static. Telescopes like the Vera Rubin Observatory will catch more long-period comets diving inward, and from their trajectories will refine our models. But that's like trying to map a city by watching only the cars that crash into your driveway. So, let's start at the very beginning of our ignorance. We don't know how many comets the solar system has already lost to passing stars and galactic tides, or how many it has quietly stolen from other systems over billions of years. We don't know how sharply the inner Oort cloud transitions from a thickened disk into a true sphere, or how lumpy that sphere is above and below the planetary plane. And yet something is above the planets. Something is below them. A whole unseen population we've never photographed directly. Future surveys, interstellar probes, even propulsion concepts we haven't built yet will chip away at this mystery. But a definitive map of our own cloud might demand technologies we haven't even imagined. Which leads to one last unsettling question. If we're this uncertain about the space right outside our door, What happens to our picture of the universe when we finally step through it? So let's walk back to where we started. That flat classroom poster. You know the one. All the planets in a neat line, the orbits drawn like train tracks. And Pluto sitting dramatically at the edge like it's guarding the border of the solar system. In that picture, once you pass the last planet, you're basically out in interstellar space. End of level. Roll credits. Now compare that to the three-dimensional model we've just built together. In reality, those planets are just a razor-thin inner layer, a tiny spinning film clinging close to the Sun. Beyond Neptune's orbit, beyond the Kuiper Belt, beyond even the scattered disk, the system doesn't stop. It swells. It transitions into this vast, dark cloud of icy worlds stretched from a couple thousand astronomical units out to almost a light year. And here's the paradox we had to untangle. Voyager 1 has already passed the heliopause. By the standards of the heliosphere, it's in interstellar space. Mission accomplished, right? Except it's only about 160 astronomical units from the Sun, sitting deep inside the Sun's gravitational domain, nowhere near the outer Oort Cloud, and nowhere near the edge of the Sun's hill sphere. By the scale of the cloud, Voyager hasn't even cleared the cosmic driveway, because here's what nobody tells you. That poster is secretly showing you only the inner few billion kilometers of a structure that extends trillions upon trillions of kilometers in every direction. We went all the way back to the collapsing molecular cloud, watched it flatten into a spinning disk, saw planetesimals form and get scattered by giant planets, and then followed the unlucky ones as gravity flung them into elongated orbits that slowly puffed into a spherical halo. The Oort Cloud isn't an add-on. It's the natural, messy outskirts of that whole process. So when you picture the solar system now, it shouldn't look like a tidy clockwork in a single plane. It's a layered, three-dimensional onion. Inner rocky worlds, outer giants, belts of debris, and then a nearly invisible sphere of icy bodies that might contain more individual objects than there are stars you can see with your naked eye. And yet, something is above the planets. Something is below them. In every direction, those orbits fill out a shell that reaches almost halfway to the nearest stars. Now let's begin looking up at the night sky with that in mind. When you stand outside and see Orion or the Big Dipper, you're not just looking at distant suns. You're looking through our own dark countryside. A silent, frozen population of comets and worlds circling our sun from so far away that their year can last millions of your years. So the question becomes, if this is what home really looks like, what does it actually mean to leave it? So the question becomes, if this is what home really looks like, what does it actually mean to leave it? To really leave, you have to go past the Oort Cloud, past the Sun's hill sphere, out into space where our star is no longer the main character. Because here's what nobody tells you. Beyond that invisible frontier, you're not in our solar system or their solar system. You're in the in-between, the interstellar medium, a thin ocean of gas, dust, and magnetic fields that threads between the stars and ties them all into the broader galactic web. Out there, the sun is just one gravity, well among many, jostling with nearby stars. Each one probably has its own distant cloud of comets, its own dark countryside. You know the one. A cold halo of worlds stretched out to a light year or more, barely bound, waiting to be nudged. Our Oort Cloud doesn't sit alone in a void. It's one bubble in a foam of overlapping spheres, all drifting through the Milky Way together. So how common are these halos really? Do most stars grow in Oort Cloud if they form in crowded clusters and trade comets with their neighbors? When we see a long period comet screaming in on a wildly tilted orbit, is it always one of ours? Or are some of them interstellar visitors, messengers that started in a completely different system and got handed off from star to star like a cosmic relay baton? Now let's begin to push the picture even further. Imagine a distant future where this isn't hypothetical, where probes or whole civilizations routinely cross from one star's halo to another. The Oort Cloud stops being an outer wall and turns into a chain of waypoints, icy bodies mined for volatiles, tiny worlds used as shelters, stepping stones between suns. Travel doesn't jump from star to star in a single leap. It creeps from one cometary halo to the next, surfing gravity wells across the galaxy. Compared to that, what we've done so far is small. Voyager 1 has been flying for nearly 50 years and is a bit over 160 astronomical units out. That's impressive. It's also deep inside the inner solar system by Oort Cloud standards, still nowhere near the edge of the sun's hill sphere. If it keeps going, it would need tens of thousands of years just to cross the region we think the outer cloud occupies. And yet, something is above the planets. Something is below them. Every new probe that samples the heliopause, every survey that spots an interstellar comet, sharpens the map. We've barely stepped off the front porch, but the picture we're drawing of that porch is already reshaping how we see our place in the universe, and what it might mean, someday, to truly leave home. So let's lock this new picture in before we head to the real finale. Because if you only take one thing away from all of this, let it be this. The solar system is not a neat, flat disk that just stops at Neptune. It's a layered structure, a stack of nested zones, all floating inside a vast, three-dimensional halo we call the Oort Cloud. So let's start at the very beginning of that stack. Close in, you've got the familiar territory, the major planets, all crammed inside about 30 astronomical units from the sun. You know the one, the classic poster where Neptune is the edge. Beyond that, the Kuiper Belt thickens things out to roughly 50 AU, with Pluto, Eris, and a whole population of icy worlds tilted above and below the main plane. Push out farther and Voyager 1 is way past all of that, sitting at around 160 AU. That sounds huge, and it is for us, but compared to the full map, it's barely off the driveway. Because here's what nobody tells you. The inner Oort Cloud probably doesn't even get started until something like 2000 AU. The outer edge? On the order of 100,000 AU, brushing up against 1 to 2 light years. In that context, Voyager hasn't left the solar system. It hasn't even reached the Voyager. Crossing the Oort Cloud at Voyager speeds would take tens of thousands of years. So when you hear interstellar space, remember, that's a statement about the medium the probe is moving through, not a clean exit from the sun's domain. That's where the heliopause comes back in. The heliopause is just the boundary where the solar wind loses its fight with the interstellar medium. It's a bubble of charged particles, not of gravity. The sun's gravity reaches far beyond that, out nearly to the edge of its hill sphere, where passing stars and the Milky Way's pull finally compete on equal terms. And that's the other crucial update. The true edge of the solar system isn't a sharp line. Galactic tides tug on the Oort Cloud. Passing stars nudge comets, tilt orbits, strip some objects away and send others plunging inward. The outer cloud is not a rigid shell. It's a fuzzy, shifting frontier, constantly edited by the galaxy around us. So the mental poster needs to change. Next time you think solar system, don't stop at the flat planetary plane. Picture a bright nucleus of planets and belts, wrapped in a huge, dim spherical cloud, all being stirred from above and below by the Milky Way itself. Because once that 3D bubble model clicks, it changes what it will mean in the next section to truly say we've left home. So the mental poster needs to change. Next time you think solar system, don't stop at the flat planetary plane. Picture that bright nucleus of planets and belts inside a dim spherical cloud, and then realize what that does to the question we started with. Have we really left the solar system at all? Because here's what nobody tells you. We celebrated when Voyager 1 crossed the heliopause, the edge of the solar wind, as if it had walked out the front door and into interstellar space. And yet, something is above the planets. Something is below them. A vast Oort cloud still wraps around us, and at a little over 160 AU, Voyager hasn't even scratched 1% of that halo. It's not out of the city. It's barely past the last big intersection. So when you hear we've gone beyond the solar system, you can now add a quiet asterisk in your head. We've stepped past the sun's magnetic bubble. Yes. But we are still deep inside the sun's true reach. Inside its gravity. Inside that enormous, invisible cloud that may stretch nearly a light year in every direction. Leaving the solar wind is not the same as leaving home. I'm curious how that lands for you. Did your picture of the solar system just stretch? Or did it snap? Which part of the Oort Cloud story surprised you the most? The size, the trillions of icy worlds, or the fact that we've never seen it directly, and yet we're pretty sure it's there from the way long-period comets swoop in on wild, tilted orbits? Tell us in the comments what your old diagram looked like in your head, and what it looks like now. If you want more deep dives that take those familiar flat textbook diagrams and peel them open to 3 dimensions, this is the moment to do the YouTube ritual. If this changed your mental picture of where we are in space, consider hitting like and subscribing so you don't miss the next time we go after another hidden structure that your school poster quietly left out. No pressure, just physics. Now let's begin your next rabbit hole. If you want to keep going, we've got a whole journey waiting. From the heliosphere's distorted bubble plowing through the local interstellar medium, to the brutal timescales of true interstellar travel, to the way the Milky Way's own gravity and tides sculpt that distant cloud around us. Check out the playlist linked on screen and in the description to keep zooming out. Because once you see it this way, you're standing on a small world, inside a thin disk, inside a vast invisible halo, inside a galaxy. And we are only just beginning to understand what home really means.